Module 30, Lecture A, Metadata Callbacks. By the end of this lecture, you will be able to enable and configure metadata routing for estimators and pipelines, route sample weights and groups through compatible workflows, and explain callback registration and propagation concepts in supported estimators. Routing setup. Enable routing. Metadata routing lets an estimator or pipeline handle extra information, such as sample weights or group labels, in a controlled way. It sends this data only to the workflow components that can use it, reducing the risk that arguments are ignored or mishandled. This makes the pipeline's communication clearer, more efficient, and more robust. Metadata routing lets a pipeline pass extra information only to the steps that need it. For example, sample weights may matter for a final classifier, but not for preprocessing, while store identifiers may help evaluation avoid bias. This makes workflows cleaner, more coordinated, and more reliable, without requiring every component to handle every piece of metadata. Metadata routing defines how metadata moves between the user, a pipeline, and its estimators. Each pipeline step should clearly state whether it accepts, ignores, or rejects specific metadata, so information reaches the right component and does not cause errors. Careful routing makes model evaluation more reliable and improves reproducibility and debugging. Python code. Enable routing. This example shows how Scikit-Learn can route metadata through a pipeline. In particular, sample weights are passed to the fitting step, and the output confirms that the model uses them during training. This setup imports the main tools needed for a simple machine learning workflow. NumPy supports numerical operations, while Scikit-Learn provides utilities for configuration, creating a synthetic classification dataset, building a logistic regression model, organizing steps in a pipeline, and standardizing features with a scaler. To use metadata routing in Scikit-Learn, enable it through the configuration settings. This lets extra information, such as sample weights, move through the machine learning pipeline to the components that need it during training and evaluation. We create a small synthetic classification dataset using Scikit-Learn's make classification function. It contains 120 samples with 4 features, 3 of which are informative for predicting the target. A fixed random state makes the dataset reproducible, giving a simple setup for observing metadata routing in later steps. We create sample weights, so Class 1 has more influence during model training. Using NumPy's conditional selection, samples in Class 1 receive a weight of 5, while all others receive a weight of 1. This helps emphasize important or underrepresented classes, especially in imbalanced datasets. The code verifies that the number of data samples matches the number of sample weights, so each sample has exactly 1 weight. If they do not match, it raises an error. This check helps ensure the training data and its metadata stay consistent. A standard scaler is used to normalize the features, but it is set to ignore sample weights because scaling does not depend on sample importance. The logistic regression classifier is then configured with a fixed random state and a limit of 300 iterations. Unlike the scaler, the classifier requests sample weights during training, so it can learn while accounting for the importance of each sample. The pipeline is built so metadata is routed only where it is needed. The scaling step ignores sample weights, while the logistic regression step requests them during fitting. This lets sample weights affect the classifier's training without being passed to the scaler. The model is trained on the feature and target data while using sample weights. These weights are passed through the pipeline as metadata and routed to the steps that can use them, such as the classifier. This lets training account for each sample's weight during fitting. To compare metadata routing effects, we build an unweighted pipeline with two stages: feature scaling followed by logistic regression. The scaler normalizes the data without using sample weights, and the classifier is set up with fixed training settings for reproducibility. This provides a baseline for seeing how the model behaves when sample weights are not included during training. The model is trained on the feature and target data without using sample weights. This creates an unweighted baseline, making it possible to compare later with a weighted fit and see how sample weights affect training and the final model parameters. We compare the classifier intercept from a pipeline trained with sample weights to the intercept from an unweighted pipeline. The weighted intercept shows how weighted observations shift the model's decision boundary, while the unweighted intercept provides a baseline. This comparison highlights how metadata routing affects model fitting. The process checks the Scikit-Learn version and confirms that metadata routing is enabled, so the pipeline can pass information such as sample weights. It then verifies that the classifier uses sample weights during fitting. Finally, it compares the rounded intercepts of the weighted and unweighted models to show how sample weights can change the learned decision boundary. This example shows how Scikit-Learn metadata routing lets sample weights pass through a machine learning pipeline. A synthetic classification dataset is weighted, so class 1 has more influence. Then, a pipeline with a StandardScaler and LogisticRegression model is trained. The scaler ignores the weights, while the classifier uses them during fitting. Comparing the weighted and unweighted model intercepts shows that routing sample weights can change the learned model. Fit metadata requests. Fit metadata requests define which extra training information an estimator can accept, such as sample weights or group labels. In routed workflows, this prevents metadata from being sent to components that cannot use it. The request tells the system whether to pass the metadata on, ignore it, or treat it as an error, helping complex pipelines train in a controlled and reliable way. In a multi-step pipeline, fit metadata should be routed only to the steps that can use it. For example, sample weights may be needed by the final classifier, but not by earlier scaling steps, while group identifiers may matter only for certain analyses. Metadata routing keeps each component's role clear, reduces errors, and makes the workflow easier to manage. Fit metadata requests make workflow assumptions explicit, such as whether sample weights are used by an estimator. Metadata routing records these expectations in the pipeline, improving reproducibility and making each step easier to understand. It also helps keep training information transparent and consistent as pipelines change over time. Python code, fit metadata requests. This example shows how to configure metadata routing during model fitting. It ensures that sample weights are passed only to the classifier, and the printed routing information verifies that this request is set correctly. This setup imports key Scikit-Learn tools for building a simple machine learning workflow in Python. It includes configuration settings, a function for creating synthetic classification data, logistic regression for binary classification, a pipeline for chaining steps, and a standard scaler for normalizing features before modeling. To use metadata routing in Scikit-Learn, enable it through the configuration settings. This lets a pipeline pass extra information, such as sample weights, to the steps that need it during fitting. Once enabled, metadata requests from pipeline components are handled and routed correctly. We create a small synthetic classification dataset using Scikit-Learn's make classification function. It contains 80 samples and 4 features, with a fixed random state of 42, so the same data is generated each time. This makes the example simple, reproducible, and useful for testing or debugging. Sample weights are created to guide model training by giving Class 1 more influence. The class labels are scaled, so Class 1 receives a higher weight. Then 1 is added, so Class 0 still keeps a baseline weight. This emphasizes Class 1, without excluding Class 0 from the fitting process. This setup uses a standard scaler to normalize the features, but tells it not to use sample weights when fitting. It then creates a logistic regression classifier with a fixed random state and a higher iteration limit, and configures the classifier to use sample weights during fitting. As a result, sample weights affect only the classifier, not the scaling step. A pipeline combines data processing steps into one ordered workflow. Here, the features are first standardized by a scaling step, then passed to a logistic regression classifier. This structure ensures the data is processed in the correct order and helps manage metadata routing consistently. Calling the pipeline fit method with features, target labels, and sample weights trains the full pipeline in one step. The weights are routed only to the classifier, since the scaler does not use them. This lets the classifier account for sample importance, which can help with imbalanced data or emphasized examples, while the pipeline handles the metadata routing automatically. We check the metadata routing for both the scaler and the classifier in the pipeline to see how sample weights are handled during training. This confirms that the classifier is configured to use the weights, while the scaler ignores them, ensuring the metadata is routed correctly. The code checks the Scikit-Learn version, then verifies how sample weights are routed through the pipeline. It shows that the scaler ignores sample weights during fitting, while the classifier uses them. The final message confirms that the pipeline was fitted with one shared sample weight input, demonstrating coordinated metadata handling across its steps. This example shows how metadata routing controls where sample weights go in a Scikit-Learn pipeline. A standard scaler is configured to ignore the weights, while a logistic regression classifier uses them during fitting, making one class more influential. The script then confirms the setup by showing that only the classifier receives the sample weights, demonstrating finer control over metadata in machine learning workflows. Score metadata requests. Score metadata requests define what extra information an estimator or pipeline can use when evaluating performance, beyond predictions and true targets. This may include sample weights or group labels, which can affect the score. Each estimator must state whether it accepts, ignores, or rejects this metadata, because scoring may require different information than training. For example, sample weights used during training may also be needed during scoring, so the evaluation reflects each observation's importance. In pipelines, score metadata requests make it clear which information should reach the final estimator during evaluation. Earlier pre-processing steps may not need details like sample weights or group labels, but the scoring step often does to produce the intended metric. Metadata routing prevents confusion by making these requirements explicit, so results reflect the planned evaluation design rather than a default calculation. Configuring score metadata requests helps keep model evaluation clear and reliable when models are reused or added to larger workflows. Proper routing ensures needed metadata is used correctly, irrelevant metadata is ignored, and unsupported data is flagged. This supports accurate performance assessment in production and research, where results can affect deployment, compliance, and evaluation strategies such as weighted scoring for financial models. Python code. Score metadata requests. This example shows how score metadata routing can use sample weights when evaluating a pipeline. It compares the reported score with and without weighting to show how sample weights can change the result. We import the main tools needed to build a simple machine learning pipeline. NumPy supports numerical work, while Scikit-Learn provides configuration, synthetic classification data, logistic regression, pipeline construction, and feature standardization. Together, these imports prepare the environment for creating and evaluating a standardized logistic regression workflow. To use metadata routing in Scikit-Learn, first enable it through the configuration settings. This lets a pipeline pass extra information, such as sample weights, through operations like scoring. Once enabled, you can configure metadata requests so that this information reaches the final estimator correctly. We create a small synthetic classification dataset with Scikit-Learn's make classification function to demonstrate model behavior in a controlled way. It contains 120 samples with 4 features, 3 of which are informative for predicting the target. A fixed random state ensures the same dataset is generated each time for reproducible results. To give the first 20 observations more influence in scoring, create a weight array the same size as the target array, with a default weight of 1 for each observation. Then, set the first 20 weights to 5, so those observations count more heavily in the weighted evaluation. We create a logistic regression model with a fixed random state for reproducible training, and allow up to 200 iterations. We also configure scoring to use sample weights, so evaluation can give more influence to selected observations when measuring performance. A pipeline combines the main pre-processing and modeling steps into one workflow. Here, the data is first standardized by removing the mean and scaling features to unit variance, which helps logistic regression perform well. The logistic regression model is then applied, with support for sample weights during scoring, so different samples can have different importance. The pipeline also ensures this metadata is passed correctly to the final model. The pipeline is first trained on the feature and target data. Its performance is then measured once without sample weights to get a baseline score, and again with weights applied. By giving extra importance to the first 20 observations, the weighted score shows how prioritizing certain samples can change the model's accuracy. The code checks the Scikit-Learn version and confirms that sample weights are being used for scoring. It then compares the model's regular accuracy with its weighted accuracy, where the first 20 observations are given extra importance. This shows how sample weighting can change the evaluation of model performance. This script shows how Scikit-Learn metadata routing can pass sample weights into model scoring. It builds a classification pipeline with scaling and logistic regression, gives the first 20 samples higher weight, and compares accuracy with and without those weights. The difference between the two scores demonstrates how weighting selected samples can change model evaluation, while the printed Scikit-Learn version confirms the setup used. Routing metadata. Sample weight routing. Sample weight routing passes observation importance through a machine learning workflow, so each step can use it correctly. These weights control how much each training example affects fitting, scoring, or evaluation, which helps when data is unevenly representative or varies in reliability. The key idea is to deliver weights only to workflow components that can properly interpret them. In routed workflows, sample weights must be passed correctly through pipelines, model selection tools, and cross-validation. Different components may use weights differently, or not at all, so routing makes each component's needs explicit. This helps ensure weights are applied during fitting and scoring when required, and prevents mistakes where weights are silently ignored. Sample weight routing keeps weighted learning fair and consistent by carrying weights through the full workflow, from training to performance reporting. These weights can correct underrepresentation in surveys, emphasize important fraud patterns, or prioritize reliable sensor data in quality control. The key idea is to treat weights as essential metadata, not as ordinary input features. Python code, sample weight routing. This example shows how sample weights move through a pipeline. Metadata routing sends the weights only to steps that can use them, and weighted training can change the final fitted classifier. We import NumPy for numerical work and Scikit-Learn tools for building and evaluating a machine learning workflow. The setup includes configuration support for Scikit-Learn, a synthetic classification data generator, logistic regression, accuracy scoring, and a train test split for fair evaluation. We also use a pipeline with standard scaling, so pre-processing and model training can be organized into one streamlined process. This setting turns on metadata routing in Scikit-Learn for the current session. It lets extra information, such as sample weights, move through a pipeline only to the steps that can use it. This gives more control and flexibility during model training. We create a small imbalanced classification dataset using Scikit-Learn's make classification function. It has 300 samples with 4 features, 3 of which are informative, and the classes are split unevenly, with most samples in one class. A fixed random state makes the dataset reproducible. To help the model learn from the rare class, we give those examples more weight during training. Labels marked as the rare class receive a higher sample weight, while all other examples keep the standard weight. This makes the rare class influence the fitting process more strongly. We split the dataset into training and testing sets while keeping features, labels, and sample weights aligned. Using Scikit-Learn's train test split function, 30% of the data is held out for testing. Stratification preserves the label distribution in both sets, and a fixed random state makes the split reproducible. The split data function separates the dataset into training and testing features, labels, and sample weights. This keeps each feature set matched with its correct labels and weights, so the data is ready for later processing and model training. Before training, the system verifies that the number of sample weights matches the number of training examples. This ensures each row has exactly one weight. If they do not match, an error is raised to protect the integrity of weighted model fitting. This pipeline combines pre-processing and modeling in one workflow. It first standardizes the features by removing the mean and scaling them to unit variance, which helps logistic regression perform well. Then a logistic regression classifier learns a separating hyperplane for the classes, using a fixed random state for reproducibility and enough iterations to support convergence. This code sets how sample weights are used in the pipeline. The scaler ignores them because feature scaling does not depend on sample importance, while the classifier requests them so logistic regression can fit the data with those importance values in mind. This is especially useful for imbalanced datasets. The model is trained using the features, labels, and sample weights from the training data. These weights change how much each example influences learning, giving more importance to the rare class, so the classifier reflects the intended priorities. We build a simple pipeline to train a model without sample weights. It first standardizes the features so they are on a comparable scale, then fits a logistic regression classifier with a fixed random state and a maximum of 500 iterations. This provides a baseline for comparing against a model that uses sample weights. The plain model is trained on the training features and labels using a pipeline with feature scaling, followed by logistic regression. The scaler standardizes the inputs, and the classifier learns how the features relate to the labels. No sample weights are used, so every training example has equal influence. The code generates predictions on the test data using 2 models, one trained normally and one trained with sample weights. The weighted model reflects the importance assigned to each training sample. These 2 prediction sets are then used to compare model performance. We evaluate the plain model by comparing its predictions with the true test labels to get standard accuracy. We then do the same for the model trained with sample weights. Finally, we calculate weighted accuracy, which includes sample weights during evaluation and gives a more informative performance measure for imbalanced datasets. The output summarizes key checks and results from the model run. It reports the Scikit-Learn version, the training set size, and the weight given to the rare class. It then compares plain test accuracy with accuracy from a model trained using sample weights, and also shows weighted test accuracy for a more balanced evaluation. This script shows how sample weights can be used in a Scikit-Learn pipeline for an imbalanced classification problem. It gives higher weight to the rare class, splits those weights with the data, and trains a pipeline where scaling ignores the weights, while logistic regression uses them. By comparing models trained with and without weights and evaluating weighted accuracy, it demonstrates how sample weighting can change performance on imbalanced datasets. Group metadata routing. Group metadata routing passes information about related records through a machine learning workflow, so each step can use it properly. This matters when records are not independent, such as repeated data from the same person or customer. In tasks like cross-validation, grouping keeps related records together, reducing data leakage and making results more reliable and transparent. Group metadata is essential in workflows that need to keep related records together, such as group-aware cross-validation. It ensures that all data from the same patient or customer stays in one fold, so the model is tested on genuinely new groups. Metadata routing makes sure these group labels reach the right parts of the workflow, reducing errors and improving transparency. Group metadata routing lets each step in a machine learning workflow receive only the extra information it needs. Pre-processing steps may ignore group labels, while validation or scoring can use them for group-aware splitting and evaluation. This keeps group information separate from the main data, supports complex model selection, and helps prevent overly optimistic results. Python code group metadata routing. This example shows how to use group labels during cross-validation. Group-based splitting keeps related records together in the same fold, and the results compare this approach with ordinary validation. This setup imports the main tools needed for a simple machine learning workflow. NumPy supports numerical array operations, while Scikit-Learn provides tools to create a synthetic classification dataset, train a logistic regression model, and evaluate it with cross-validation. It also includes standard and group-aware fold splitting, a pipeline to combine pre-processing with modeling, and feature standardization to help logistic regression perform well. We create a small synthetic classification dataset with Scikit-Learn's Make Classification function. It contains 120 samples with 6 features, 4 of which are informative for predicting the target. A fixed random state ensures the same data is generated each time, making it useful for testing classification models with features of varying relevance. This creates group labels with NumPy by making 30 group identifiers from 0 through 29 and repeating each one 4 times. The result is 120 labels with 4 related records in each group. This structure is needed so group-based cross-validation can keep related records together. The process first verifies that the number of group labels matches the number of target labels, so each sample has exactly one group. If they do not match, it raises an error to signal a data structure problem. This check helps protect the reliability of group-based cross-validation. The pipeline combines 2 steps for model training. It first standardizes the features by centering them and scaling them to unit variance, so they are treated more evenly. It then applies logistic regression for binary classification, using enough iterations to support convergence, and a fixed random state for reproducible results. The pipeline uses only the features and target, without incorporating group labels. Use group-based cross-validation with 5 splits to keep related records in the same fold. Then, evaluate the model with the cross-validation scoring function, using the features, target, group labels, and group-aware splitter. This estimates accuracy while respecting the group structure and helps prevent data leakage between training and validation data. A 5-split K-fold cross-validator divides the data into 5 parts, using each part once for testing while training on the rest. Shuffling randomizes the data before splitting, and a fixed random state makes the results reproducible. Cross-validation then evaluates the model across these splits, using the features and target, treating all samples as independent and ignoring any group membership. To check for group leakage, create one split with the GroupKFold splitter and compare the group labels in the training and testing sets. If the 2 sets of group labels have no overlap, then no group appears in both sets, confirming that the group-based validation split is valid. The process checks the Scikit-Learn version for reproducibility, then verifies that grouped cross-validation keeps related records out of both training and testing sets. It reports the model's average accuracy with group-aware validation and compares it with ordinary cross-validation that ignores groups. This comparison shows how accounting for group membership affects the model's measured performance. This script compares group-aware cross-validation with ordinary cross-validation in Scikit-Learn using a synthetic classification dataset. It shows that group-aware splitting keeps all samples from the same group together in either training or testing, which prevents data leakage. A scaled logistic regression pipeline is evaluated with both methods, and the first split confirms that no groups are shared when group-aware validation is used. The reported mean accuracies illustrate why group membership can matter when estimating model performance. Metadata aliases. Metadata aliases let different parts of a machine learning workflow refer to the same supporting data, such as sample weights or group labels, even when they use different names. They translate these names without changing the data's meaning, helping metadata move correctly through pipelines and model selection. This keeps complex workflows clear, consistent, and functional. Metadata aliases help machine learning workflows pass the right information between preprocessing, model fitting, and evaluation steps, even when components use different names for the same data. They can map labels for items like patient visit groups or sample weights, so validation and training behave correctly. This reduces manual fixes and makes the workflow more efficient and less error-prone. Aliases make workflows clearer by controlling which metadata each component receives. For example, one component may use group information, while another only needs sample weights. This prevents metadata from being sent to the wrong place and makes workflows easier to inspect, debug, and adapt, especially in team settings. Python code. Metadata aliases. This example shows how metadata aliases work in routing. Aliases let external metadata names be translated for an estimator, enabling weighted fitting through the mapped name. We import key Scikit-Learn tools needed to build machine learning workflows in Python. These include a configuration function for global settings, base classes for creating estimators and classifiers, and the pipeline utility for chaining processing steps into a streamlined workflow. To use metadata routing in Scikit-Learn, first enable it through the configuration setting, This prepares the library to handle metadata aliases, which connect external metadata names to the estimator parameters they should control. Enabling it before setting requests ensures metadata is routed correctly in the rest of the code. The alias demo classifier is a simple scikit-learn style classifier that defines a fit method for training. During fitting, it records the sorted unique classes from the target values, stores the total of the provided sample weights, and sets a majority class using the first class in that sorted list. The method then returns the classifier instance, so it can be used in chained calls. The predict method returns the majority class found during fitting for every input example. This means all predictions have the same value, regardless of the input features. In this example, the goal is to demonstrate metadata routing rather than accurate prediction. A small in-memory dataset is created to demonstrate metadata routing. It includes simple input values, matching class labels, and sample weights that indicate each example's importance during model fitting. This compact setup makes it easier to see how metadata aliasing works in practice. We create a custom classifier that can handle metadata during fitting. It is set up to accept sample weights through an external alias called importance. This shows how Scikit-Learn can use metadata aliases to pass the same information under a different name. A pipeline is created with one step, the model, which uses a custom classifier. When the pipeline is fitted to the data, it routes the metadata named importance to the classifier as sample weight. This shows how Scikit-Learn can use metadata aliases to pass sample weights to the right component. The fitted classifier is accessed from the pipeline, so its trained model can be inspected directly. The output then checks the Scikit-Learn version and shows that the external metadata name, importance, was mapped to the estimator's internal sample weight parameter. Finally, the summed weights confirm that the alias successfully passed the intended metadata to the estimator. This script shows how Scikit-Learn metadata routing can use aliases to pass information into a model. A custom classifier records metadata during fitting, while an external name, importance, is mapped to the internal sample weight parameter. When the pipeline fits the model, it forwards the weights through this alias, and the classifier reports their sum. The output confirms that the alias correctly delivered the sample weights. Callback routing. Pipeline callback routing. Pipeline callback routing. Make sure callback information reaches only the appropriate stages in a multi-step estimator workflow. Unlike a simple estimator, where callbacks can be attached directly, a pipeline must coordinate stages such as pre-processing and prediction. It checks the callback metadata and forwards it only to components that can use it, such as a final model monitoring validation performance. Pipeline callback routing sends each callback instruction to the estimator that can use it correctly, much like directing information to the right department. A training loss callback should reach the iterative fitting step, while feature logging should go to the transformation step. This routing helps complex pipelines, including nested components, preserve the meaning of information as it moves through the workflow. Pipeline callback routing lets supported estimators pass callbacks through a workflow in a controlled and predictable way. Instead of manually attaching callbacks to each step, users can register them at a higher level, while each estimator declares which callbacks it can handle. This makes workflows easier to reuse, inspect, and refactor, especially for tasks like training monitoring and logging. Python code. Pipeline callback routing. This example demonstrates callback routing in a pipeline. Metadata is passed only to steps that can use it, and the output confirms that callbacks are propagated selectively. We import key Scikit-Learn tools for building a machine learning workflow in Python. These include base classes for creating custom estimators and classifiers, a pipeline tool for chaining pre-processing and modeling steps, and a standard scaler for normalizing features. We also load the iris dataset, a common example dataset used to demonstrate machine learning techniques. The training callback class records what happens during training. When a new callback object is created, its initialization method sets up an empty events list. This list stores messages showing which parts of the training pipeline received the callback, making it possible to review those interactions later. The record method adds a new event to the event list by combining the step name and its message. This creates a simple log of which pipeline step received a callback and what message came with it, making the callback flow easier to track. The callback classifier is a Scikit-Learn compatible classifier that follows the standard estimator interface. During fitting, it records the sorted set of target classes and chooses the majority class based on the most frequent label. If a callback is supplied, it logs that the callback was received during fitting. The fitting process then returns the classifier instance for continued use. The predict method returns one prediction for each input item by assigning the majority class found during fitting. In other words, it labels every input with the most common class, providing a simple baseline prediction strategy. We load the iris dataset from Scikit-Learn, a small and familiar dataset often used to demonstrate machine learning. Then, we use the first 30 flower measurements and their matching species labels to create a simple subset for quick experimentation. Before training, the code checks that the feature data and labels have the same number of rows. This confirms that every data point has a matching label, which supervised learning requires. If they do not match, it raises an error, so the data can be fixed before the model is fitted. This pipeline combines two steps. First, a standard scaler normalizes the features by centering them and giving them unit variance, and then a custom callback classifier fits the model. The classifier can receive a callback during training to record events or messages. Using a pipeline keeps pre-processing and modeling organized, while ensuring the callback is sent only to the model step. Create a training callback object to record events during model fitting. Then, fit the pipeline using the feature data and target labels, passing the callback only to a model step. This routing ensures the final model receives the callback and can log relevant training events. The example checks the Scikit-Learn version, summarizes the pipeline structure, and reviews which steps received the callback. It shows that the scaler did not receive the callback, while the model did. This confirms that callbacks are routed only to compatible pipeline steps, and that selective routing worked as intended. This example shows how a callback can be routed only to the pipeline step that supports it. In a Scikit-Learn pipeline with a scaler and a custom classifier, the callback is passed during training but received only by the classifier. The logged output confirms that the scaler ignores it, while the model step records it. This demonstrates selective metadata forwarding to compatible pipeline components. Registering callbacks. Registering callbacks means telling an estimator which external handlers should be involved at important points in its operation. This defines when the callback is notified, what data it can access, and how that data should be used. Callbacks can support tasks like tracking training progress, early stopping, or monitoring group performance under metadata rules. In short, registration makes the callback an active part of the estimator's metadata flow. A clear callback registration process defines what each callback does and which metadata it needs. Some callbacks only need basic event information, while others require details such as sample weights or group labels. Keeping these needs separate helps supported estimators route metadata correctly, so each callback receives only the data it should use. This improves transparency and prevents hidden or unintended data flow. Registering callbacks with clear rules helps complex workflows run predictably. In pipelines or composite estimators, callbacks may need information from several stages, such as pre-processing or validation, so they must receive the right metadata at the right time. This prevents misuse of information, makes debugging easier, and supports consistent behavior across different models. Callback propagation. Callback propagation in machine learning passes a callback from an outer workflow to the inner components that can use it. This matters in pipelines or composite estimators, where training events may happen inside a classifier or transformer, rather than at the top level. Proper propagation lets the system forward callbacks automatically, but only to components that support them. Callback propagation means sending a callback only to the parts of a machine learning model that can use it. In complex models, some sub-estimators may understand the callback, while others do not, so routing it selectively prevents misuse. This keeps workflows clearer, more efficient, and aligned with each estimator's capabilities. Callback propagation helps make machine learning systems reproducible, debuggable, and easier to monitor. When callbacks are not passed consistently, they may work in a single model but fail inside a pipeline, leading to missing logs or missed actions. Supported estimators avoid this by routing callbacks only to components that are designed to handle them, making callbacks a formal communication channel within the estimator hierarchy. In this lecture, you learn to enable and configure metadata routing for estimators and pipelines, route sample weights and groups through compatible workflows, and explain callback registration and propagation concepts in supported estimators. In the next lecture, Lecture B, we will go over inspection displays.
Thank you for your attention. See you all in the next lecture.